All right, let's just jump right into this explainer and trace the absolutely thrilling, century-long journey of general relativity. I mean, it is an incredible story. We're talking about how a single theory predicted an inescapable dark star, got nearly destroyed by a literal mathematical monster, and was ultimately reborn to completely change our understanding of the cosmos forever.
Now, despite its intimidating, mind-bending reputation, the theory's foundations actually start with beautifully simple ideas that, honestly, we can all grasp. As Einstein himself pointed out, you really don't need to be a theoretical mathematician to understand the core concepts. You just need a willingness to think differently about the world around you.
To really get this paradigm shift, we first have to contrast it with what came before. For 2.5 centuries, Isaac Newton's laws absolutely ruled physics. You know the drill. Newton saw space as this rigid, straight grid, and time as a universal ticking clock that was exactly the same for everyone, everywhere. But Einstein, he proposed a radically intertwined four-dimensional universe where space is actually curved and time is completely relative, meaning it literally slows down the closer you get to a massive source of gravity. Mind-blowing, right?
So imagine space-time, not as some empty, invisible box, but more like a giant block of jelly. When you place a supermassive object, like our sun, onto this jelly, it warps and distorts the area all around it. That curvature, that physical dip in the jelly, is exactly what we feel as gravity. It forces everything, from orbiting planets down to perfectly straight shooting rays of light, to follow its curved path. The spark for this entire revolution was just a brilliant flash of insight. In 1907, Einstein was just sitting at his desk at the patent office in Bern when suddenly he realized that if somebody was in free fall, they simply wouldn't feel their own weight. This one epiphany about weightlessness basically became the lighthouse guiding his entire theory. And it's so true that today, modern scientists actually prove this by dropping objects in massive vacuum towers in Germany. Literally watching gravity just seem to disappear right before their eyes as the scales drop to absolute zero. But, having a brilliant idea is one thing. Actually proving it mathematically is a whole other beast. Moving to Zurich in 1912, Einstein embarked on 8 grueling years of monomaniacal work. The math required to describe this curved universe was so unbelievably complex that he had to rely heavily on the geometric genius of his old friend Marcel Grossmann. Together in these Zurich cafes, they worked endlessly, just grinding to overcome these seemingly insurmountable mathematical obstacles.
And after all those years of obsessive calculation, in 1915 they produced this single, elegant equation. It's really just a few symbols on a page, but it perfectly described the entire architecture of our universe. Actually, it immediately proved its worth by perfectly predicting the perplexing, shifting orbit of the planet Mercury, something Newton's classical laws had completely failed to do. A real game changer.
While the theory was published pretty quietly in 1915 during the absolute chaos of World War I, the real physical proof came in 1919. British astrophysicist Arthur Eddington led this daring expedition to photograph a solar eclipse. And sure enough, he proved that the sun's gravity actually bent the light from distant stars, exactly as Einstein's math predicted. This single, astonishing physical confirmation launched Einstein straight to global icon status. The atmosphere when Eddington presented these findings in London was, well, it was as tense as a Greek drama. Standing right beneath the portrait of Isaac Newton, Eddington compared Einstein to Napoleon, but with a really beautiful difference. He noted that while emperors were makers of empires whose hands were stained with blood, Einstein was quite literally a maker of universes. But right at the absolute peak of Einstein's glory, a letter arrives from the muddy trenches of World War I. A German physicist and soldier named Karl Schwarzschild had managed to solve Einstein's equations for a single star. It was a titanic achievement for sure, but it exposed a terrifying, hidden flaw in the math that would soon threaten the theory's very existence. This mathematical flaw became known as the Schwarzschild singularity. It was a literal point in the equation where division by zero resulted in infinity. Mathematically, it created an impenetrable black bubble where space and time simply ceased to exist. To put that into perspective, to even make this visible in our solar system, you would have to condense the massive bulk of our entire sun down into a tiny sphere just 3 kilometers wide. Just unimaginable density. Well, the theoretical became intensely personal during a 1922 conference in Paris. French mathematician Jacques Hadamard aggressively confronted Einstein in front of the whole audience, pointing directly at this fatal mathematical flaw. Hadamard declared that at this singularity, the equation just completely falls flat on its face.
It was literally the end of the world in equation form.
The nightmare only worsened when astrophysicists started really looking at the life cycles of actual stars. They realized that massive stars eventually run out of nuclear fuel, and when they do, gravity wins. The star shrinks, its atoms and nuclei forcefully collapse inward, eventually crushing down to a point of zero radius. So this meant that this terrifying mathematical singularity might actually manifest in physical reality.
The idea was so deeply disturbing that the scientific community went into sheer denial. I mean, even Einstein himself flat out refused to believe it. He felt nature just shouldn't behave this way. He even wrote a paper, which his peers later called the worst he ever published, honestly, specifically trying to bend the math to prove that these implosions, these dark stars, were physically impossible.
Because of this mathematical monster, the theory of relativity was largely abandoned by the broader physics community for decades. Einstein actually died in 1955 doubting his own creation. But science marches on. A new generation of brilliant British scientists in the 1960s would soon pull relativity back from the abyss and prove Einstein right all along.
The major theoretical breakthrough came from Roger Penrose. He had a sudden, brilliant epiphany while casually crossing a street in London. He realized a mathematical theorem involving what he called a trap surface, basically a point of no return where a collapsing star focuses all its light completely inwards. Penrose definitively proved that a star collapsing into a point of infinite density, what we now call a black hole, is a real mathematical inevitability. Meanwhile, physical proof was about to emerge from a completely unexpected source. In 1967, a young astronomer named Jocelyn Bell Burnell, who had spent her early career literally swinging a sledgehammer to build a massive radio telescope in a field, detected something impossible. Through the freezing cold night, she recorded a rapid, perfectly timed string of pulses from the deep sky. Just pulse, 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 pulse. Her eureka moments proved the existence of pulsars, or neutron stars. We're talking about incredibly dense dead stars holding the enormous mass of our sun inside a ball just 10 kilometers across. Finding these extreme objects validated the exact kind of physics required for black holes to exist. Simply put, if a neutron star was possible, a black hole was definitely possible.
Now imagine what happens if you actually try to visit one of these incredibly dense neutron stars. The gravity is so immense it literally bends light over the horizon, allowing you to see the back of the star. It dramatically slows your watch due to time dilation, and if you try to land on it, the gravitational pull on your feet would be so much stronger than on your head that it would violently stretch and tear your body apart. It's a gruesome process that astrophysicists actually call spaghettification. But neutron stars are really just the appetizer. What actually happens if we try to cross the horizon of a true black hole? Since we now know they physically exist, we face a terrifying barrier. The edge of a black hole is a one-way trap you never get out of. Light can enter, but it can never, ever leave. Anything that falls in gets completely swallowed and its information seems lost to the universe forever, a concept that makes modern physicists highly uncomfortable.
And this brings us to the ultimate uncharted frontier of modern physics. General relativity beautifully and perfectly describes the infinitely large macro-universe. But at the dead center of a black hole, at the singularity, the fabric of space-time completely tears, and Einstein's math just breaks down entirely. To understand that subatomic center, scientists are forced to try and merge relativity with the rules of the incredibly small, quantum mechanics. The attempts to merge these two fields are yielding some truly mind-bending ideas. One fascinating new theory by physicist Carlo Rovelli suggests the black hole doesn't actually collapse forever. It hits a quantum limit and bounces back, exploding in milliseconds. But here's the catch. Because of Einstein's extreme time dilation near such massive gravity, that millisecond bounce looks to us on the outside like it's happening in extreme slow motion, literally taking billions of years to explode.
As we attempt to unite these grand theories of the cosmos, we really share the humbling sentiment of Isaac Newton, which was later echoed by Einstein. Newton once said he felt like a child on a beach, playing with a few beautiful pebbles, while the immense, vast ocean of all the things he was yet to understand lay completely unexplored right before him.
And that leaves us with the ultimate question. What really is the passing of time? If the new equations for quantum gravity actually have no time parameter in them at all, then time itself might not even be a fundamental ingredient of our universe. So what exactly is time then? And what magnificent new universe of understanding awaits us just over the horizon?